All right. Hello, everybody. Welcome back. For us, it's been half an hour. Hopefully, for you all, it's been a little longer. We are finishing up 5.1, doing some 5.2. A lot of this is like very familiar stuff. I think we will probably get to the affine communication limit in 5.3 today. I don't know. We're not. I'm not going to overthink it. We're just going to do what we can. So, okay. Last thing we said, a topological space is quasi-separated if the intersection of any two quasi-compact opens is quasi-compact. This led to a theorem about affine opens, and kind of like an alternative definition almost that a scheme is quasi-separated if the intersection of two affine opens is a finite union of affine opens. So, kind of, our next theorem is that, well, affine schemes are quasi-separated. And, yeah, this makes a lot of sense,
Yeah,
right? Like, I don't think this needs a ton of justification. This seems like
no.
a very implicit thing. Um, yeah, I don't think that needs any further justification.
No.
Um, okay, so now I think this is going to be a less trivial theorem because there's exposition after it. So scheme X is quasi-separated if and only if there exists um, a cover of X by affine opens any two of which have intersection also covered by a finite number. So I want to highlight where this comes to be sort of difficult is showing that there exists a cover um, of affine opens, right? So like the tough part here is quasi-separated implies existence of a cover, and then this bit is for free. Um, but I don't even know. Like maybe it just comes from this definition. So I don't know. This also seems like a kind of trivial one. Um, yeah, I kind of take back what I was like. Maybe this is just easy, right? Maybe we get a
Huh.
cover of Affine Opens for free. Um, and then quasi-separated definitely implies the whole
Yeah.
um, intersection is quasi-compact. Um,
Right.
yeah, yeah. I don't even
Yeah.
think that. So the one direction is easy. The two direction is a little bit less easy. So we want to show the intersection of any two quasi-compact opens is quasi-compact. And so what we want to say is we want to take two quasi-compact opens, intersect them, and then they're covered by a finite number of affine opens, and that's a finite subcover. So actually, no, that is also easy. Um, we will see that quasi-separatedness will be a useful hypothesis in theorems in conjunction with quasi-compactness, and that various interesting kinds of schemes, affine, locally Noetherian, and separated, respectively, are quasi-separated. This will allow us to state the theorems more succinctly. For example, if X is quasi-compact and quasi-separated, rather than if X is quasi-compact and neither this thing or that thing holds. Quasi-compact and quasi-separated means something concrete. So X is quasi-compact and quasi-separated if and only if X can be covered by a finite number of affine opens, any two of which have intersection covered by a finite number of affine opens. And this is by definition, right? So basically this is like just the nicest possible scheme to work with,
Yeah.
at least as I understand it. Maybe adding on Noetherian QCQS. So when you see quasi-compact and quasi-separated as hypotheses in the theorem, you should take this as a clue that you will use this interpretation and that finiteness will be used in an essential way, right? So the implication here is that finiteness matters to the theorem or whatever we're talking about.
Yeah.
The combination of hypotheses is so common that people describe it as QCQS. So, yeah. Okay. Theorem. All projective A schemes are QCQS. Well, you know, Pn over A is equal to proj of A over x0 through xn. And then we'll just say mod the zero ideal. And then if we wanted to get a different projective scheme, we would just say like mod something legitimate. And then equivalently, do we need to use? It has a hint about graded rings, but like, duh. So then there exists an affine line. On proj A over xi. Right?
Yeah.
And then the intersection of these affine lines, intersection of a xi 0, which is finally covered. And n plus 1, many of these. Wow, that did not write. So yeah, that was not difficult.
Yeah.
Um, okay. An example of a non-quasi-separated scheme. If we take X to be spec of infinitely many things, and let U be X mod this, where M is the ideal generated by X1, and so on. Take 2 copies of X, glue along U by a wedge sum. This is affine infinite space with a doubled origin. So affine space with doubled origin. This is not quasi-separated. Since basically we can't cover 0 finitely. Does that make sense?
Yes.
Okay. One very important topological notion is dimension. It is amazing that this is a topological idea. But despite being intuitively fundamental, it is more difficult, so we postpone that until chapter 12. Okay. Any questions on this section before we move into 5.2?
No.
Okay. Reducedness and integrality. Recall that one of the most alarming things about schemes is that functions are not determined by their values at points, and that is because of the presence of nilpotents. And we talked about this in terms of the nil radical. So definition, we say that X is reduced if its stalks have no non-zero nilpotents for all P. Reducedness is by definition a stalk local property. And so we had this theorem, with the no radical like forever ago. Not even sure where that would be. Well, I know where it is in the book, so let me find it in the book. Because I want to find the actual thing. Yeah, so page 75. Functions are not determined by their values of points, the fault of nilpotents. Yeah. Ring elements that have a power that is 0 are called nilpotents. Um, the nilpotents form an ideal called the null radical. Um, is the intersection of all prime ideals. Geometrically, a function vanishes. A function on spec A vanishes at every point if and only if it is nilpotent. So I'm just gonna write a bunch of this down. As a recall, nilpotent equals intersection of prime ideals. And then equals element um, with a power equal to 0, and then f in spec A vanishes everywhere if it is in nilpotent. Okay. And then because of this, we had the associated thing that if nilpotent or if the no radical is the just the 0 ideal, then functions are determined by points. Okay. So now we get to the theorems about reduced, and this is equivalent to the no radical of structure sheaf is just 0 ideal. Okay. So theorem. Um, if f and g are functions, aka global sections on ox, on a reduced scheme that agree at all points, then f is equal to g. And this is very reminiscent of something we did do in Hartshorn because we're about to define regular functions and rational functions, and you're going to see that all of this is just like a very technical
Can
way
you
of
mind
talking
going back
about.
up real quick?
Yeah, a very technical way about talking about things that we've seen repeatedly. But this is kind of like our gluing lemma from when we
Yeah.
started Hartshorn. Um,
Thank you.
of course. So, proof sketch. Um, was that the ring of regular functions injects to the product. Oh no, the global section over U. Sorry. To the sheaf of stocks. Um, And then we can say that, F equals G as collectively evaluated at each P in U on OXP, and then let U be the entire set. And then the important thing is that since the no radical of ox is just 0, then F equals G at P in ox implies that F equals G. So this one kind of falls out of definitions and nice things, basically.
Yeah.
Does that make sense the way I wrote it down?
Yes.
Cool. Okay. So, another theorem. So, a ring is reduced if it has no non-zero nilpotents. So A is a reduced ring if and only if spec A is reduced, i.e. X is reduced if OX U is reduced for every U open in X. And so this is very much implicit to this proof sketch up here, because what we're really saying in this line is that the no radical of OXP is 0, and that the union over P in U, or really P in X, is 0. And so as long as that happens on the A ring level, we don't get new things in spec A that are nilpotent, and vice versa, right? So we have the correspondence between A and spec A with prime ideals, and irreducible points, and so these things correspond, and then no radicals correspond as well. Does all of this click?
Yes.
Cool. All right. So a corollary of this is that affine n space over a field and projective n space over a field are reduced schemes. And this is easy. When we think about the nil radical, we're working over an algebraic closure. Well, an algebraic closure is implicitly reduced. We don't have like zero divisors under multiplication. And so yeah, basically proof is K is reduced since algebraically closed. And that's it. Right, by the theorem above, then the scheme is closed, or is reduced. As an example of a non-reduced scheme, spec K over XY mod the ideal y squared xy is non-reduced. When we sketched it earlier, we indicated that the fuzz represented non-reducedness at the origin. And so, if you recall, this is equivalent to saying that um, we have a common zeroing. Um, I guess that would be that. And then we have everything, right? We have the whole
Yeah.
plane. And so we get fuzz at the origin. And then that fuzz at the origin is what lives in the null radical. And we're going to work through this in the next exercise. So I guess this leads to showing that that k of x, y local or mod y squared xy localized at x has no non-zero nilpotent elements. Um, and so if we take away the x equals 0 case, we have shared zeros between y squared and y, but we lose the fuzz at x. So when we're looking at all the spots where this is invertible, these are all of the functions of the form, you know, like 1 over x, y over x, or I guess x to the k for some k, some positive k. Um, and then x. No, it can't be x. I think that might be it. I think these are the because anything else would no. I think we can have x over x to the k, but then it's just x to the k minus 1, right? Um, and so implicitly, the smallest thing that this could be would be 1. Um, and then that should be it. And of course, times some scalar. Um, and then yeah, no power of like 1 over x to the k times m. Oops. Or y to the m, x to the km, or 1 to the m are all non-zero. Right? And so what we get out of excluding the x equals 0 case when we localize is this lack of nilpotence, which shows that the only time it ever could have happened was if we did not exclude the x equals 0 case. Um, So the only point with a non-reduced stalk, so this is kind of like another remark, that 0, 0 in spec is the only point with a non-reduced stalk. Okay, well, so what does this look like? Well, OX, and then we need P associated to 0, 0 is the set of prime ideals x minus 0, y minus 0. Um, which looks like, x, y, x plus y, anything x times f of x, y, y times f of x, y, x plus y times f of x, y. And then is this non-reduced? Yes, because we can get stuff where any of these linear combinations to some power mod the ideal x comma y reduces to 0. Does that make sense?
Yes.
Yeah. Okay. Okay. If X is a quasi-compact scheme, it suffices to check reducedness at closed points. So this is the theorem. If X is quasi-compact, it suffices to check reducedness at closed points. It says we don't need to prove that.
Right.
So we will see in exercise 6.6 that reducedness is an open condition for locally Noetherian schemes, but in general, reducedness is not an open condition. So you may be able to locally, or no, you may be able to identify the underlying topological space of a scheme with that of the spec of the complex plane over X, and then to show that the non-reduced points of X are precisely the closed points corresponding to the positive integers. The complement of this set is not Zariski open. Okay. I don't think that that is super important. Um, let's see. Warning for experts. If a scheme is reduced, its ring of global sections is reduced. However, the converse is not true. Okay. Uh, okay. Theorem. If X is quasi-compact and F vanishes on all of X, then there exists n with f to the n equals 0. This may fail if X is not quasi-compact. Hint, take an infinite disjoint union of spec AN over the dual numbers. So I'm going to call this a proof sketch. Yeah. I mean, okay. First part of this is the definition of being in the no radical. Namely, if f is 0, then n equals 1. If f is non-zero, then f is just in the no radical of x. Just by definition. And then the example for failure if it's not quasi-compact is take an infinite disjoint union I and I of and in I of spec an, where an is not necessarily the dual numbers, but the n dual numbers. And maybe I think we can even just do n equals 1 to infinity. Right? Then this is definitely not quasi-compact, but we can get a definitive f, which is going to vanish on all of x and not have an n for which f to the n equals 0. And that thing is just epsilon. Right? Because for every epsilon to the n, there's not a finite n that we can pick. Right? Like n would have n equal to the least common multiple of c. Right? So there is not an n in this case that makes this true. Does that make sense?
Yes.
Okay. Definition. X is integral if it is non-empty and ox u is an integral domain. For every non-empty open u of x. Okay. So let's try and find a trivial example, an example that breaks it, and Yeah. So example number 1 is maybe like spec R is integral. Since over any open neighborhood has, let's just say has R over X integral domain. And this would even hold for spec Z, right? We could replace R with Z. Right, that's our canonical integral domain. An example that is not integral would be like spec Z mod 6 is not integral because O of Z6 over X on, I don't know, like 2, the open subset of the discrete topology containing 2. Can have 2 cubed equals 0. No, not 2 cubed, but 2 times 3, which 2 to the 4th? Wait. I'm gonna make this 2 squared, and we're gonna pretend like that. There we go. As 2 squared equals 0. And this is a well-defined function on Z over X. Okay, so a scheme X is integral if and only if it is irreducible and reduced. So theorem X is integral if and only if it is irreducible and reduced. So we picture integral schemes as one piece, no fuzz. All right, so if it's integral, then
Tim, what do you mean if it's irreducible reduced?
and reduced.
Oh,
Does that clarify?
not really.
Okay.
Just had something be reduced
If
and irreduced.
X, like, okay, so irreducible means there do not exist U and V closed in X with X equal to U union V.
Yeah.
And then reduced means its stalks have no non-zero nilpotence for all P.
Okay, that makes sense.
And then integral means that OXU is an integral domain. for all U open in X. So now does this make sense?
Yes, it does now.
All right, so let's tackle direction 1. So let OXU be an integral domain for all U X. Then we want to show that there do not exist closed subsets. I'll have to call them, let's call them C1, C2 closed in X with C1 union C2 equals X. And then we also want to show that the stalks have no non-zero nilpotents at all points. So tackling 1, it's an integral domain OX U is equal to the union of P in U of OXP. And we're given that OX U is ID, and then this implies that OXP is an ID for all P in U. And then we want to take this integrality to the idea of closure. So I don't know, it might be easier to tackle the nilpotence thing first. So if we have a bunch of germs, then we want to consider the no radical of OXP is the intersection of prime ideals. Which is not empty if and only if. Well, this is what we want to say, is that it's not empty if and only if zero divisor somewhere. Right? Well, that's tough. Not really. Right? Because if there were a zero divisor somewhere, zero divisor in P implies P not prime. And so intersection of primes of ox p is empty set. And I'm hand waving here, but I think that this is the right train of thought. Correct me if I'm wrong.
Yeah, I like it.
Okay. And then to get the irreducibility piece, I'm not exactly sure how to get irreducibility here. Um, hmm. Hmm. So what do the closed sets in X look like? Well, the closed sets in X look like vanishings. So we want two functions such that their vanishings are the whole scheme. And we want to be able to say that this corresponds to the does not vanish set somehow, which is an open. And we want to say that the structure chief on the does not vanish set is an integral domain for both of these. Hmm. I don't know. Is there another theorem that we already have?
Tim, I'll be right back.
Okay. Mhm.
All right, I'm back. Sorry, I just had to grab something from my mom.
No, no worries. Well, we want to be able to say that. Hold on, hold on, hold on. So ox, the structure sheaf, should be equal to the union of the structure sheaf on the vanishings. And these don't have to be integral domains, but this is the complement of ox VF1. And this is ox VF2 complement. Hmm. I'm not really sure where to go from here, to be honest.
Yeah, me neither.
So, okay, I guess let's try the backwards direction for a little bit while we let that simmer. So, if we start with irreducible and reduced, um, we know that we can't break it up into two closed sets. And we know that functions determined on stalks are unique. And we want to show that the structure sheaf on any open subset is an integral domain. And whatever the trick is for this first part about zero divisors corresponding to no radicals, that's going to force the reduced implies integral, I think. Maybe it comes together with the irreducible piece. Maybe it's like you would have to break each u and v and their complements apart. I don't know. I'm not very happy with how this proof is going. um, hmm. I might bump this off to something that we can check, like something I'll work on today and maybe start up tomorrow's lecture with. Because
Okay.
this might just be one that takes more time um, to work on. So, to be continued. Um, yeah. Okay, so a presumably related theorem is that spec A is integral as a scheme if and only if A is an integral domain. Um, and I think that this just hinges off of this last one. Um, well, maybe not. So spec A is equal to prime ideals and their topology and their structure sheaf. And integral domain. Let me try Googling something. I'm just curious about something. Hmm. Yeah. Oh, I have discovered something.
Yeah.
The thing that we need for part two is that d of f1 intersect d of f2. This is empty set. And so then to show that spec A works nicely, um, so the stock, okay, first of all, the stock at P of spec A is isomorphic to the localization of A at P. And we knew that. So this gets us reduced scheme. And then the second part is that spec A is irreducible, and namely df intersect dg is equal to dfg, which we want to show is 0. And let me highlight that because it's not given whatsoever. So this is a want to show. And so since integral domain, if f is non-zero and g is non-zero, then fg is non-zero. And so fg is not nilpotent. Right?
Yeah.
And then the trick here is the same, that d of f1, f2. Right, so this is a want to show. And then what it really is df1, f2, and it's the same trick. F1 is non-zero, is, you know, is not nilpotent. And since it's not nilpotent, then we don't get 0, and then this is not the case. So there is a proof. I will write that up better, and I will start tomorrow's lecture with that better proof. However, the idea is this piece here. Um, does that make sense?
Yeah.
So, going back down here, yeah, FG not nilpotent means that the vanishing of F union the vanishing of G is not all of spec A. Okay. Um, so this is direction 1. And then, no, that's the backwards direction. This is the backwards direction. This is showing that spec A is reduced, or spec A is integral. And then to go vice versa, if spec A is integral, then it's reduced and irreducible. And since O spec A comma P is equal to AP, has no nilpotence, then A localized to P implies that A has no nilpotence. And so then multiples of primes, basically since all numbers are either primes or the product of primes, or rather the products of powers of primes, since we don't have any nilpotent elements, the only way you could get 0 is by multiplying by 0. There aren't 0 divisors. Although that is admittedly not a very, like, if we claim that 0 is equal to AB, where A and B are both non-zero, and A is a power product, B is a power product, but something in one of these without loss of generality A needs to have, C to the n equals 0. It implies nilpotent, which is a contradiction. Does that make sense?
Yeah.
Okay. So, theorem slash definition. If X is an integral scheme, then X being irreducible has a generic point. Little eta, not to be confused with the big null radical that I have. Then if spec A is any non-empty affine open of X, then box at eta is naturally identified with the fraction field of A. This is called the function field K of X of X. It can be computed on any non-empty open subset of X, as any such open set contains the generic point. The elements of K of K of X are called rational functions on X. And this is stuff we've seen in Hartshorn. Um, and this natural identification is hopefully very clear. So anything vanishing like on the generic point vanishes as the function field.
Okay.
Because the generic point is like,
Yeah.
yeah. Um, okay. Um, theorem. This really is not a theorem. This is a definition. um, theorem. If x is integral, the restriction maps from u to v. If v is not empty. And then spec A is a non-empty affine subset of X, and thus A is an integral domain. The natural map oxu to ox at eta, which is the function field, is an inclusion. Okay. So, first of all, the stalk at the empty set is the generic point. So it can't be an inclusion. The stalk anywhere else, where presumably V is contained in U, has to be an inclusion by just how the structure sheaf works. And then if spec A is a non-empty affine subset, then restricting to the function field of A is an inclusion because you just send OXU to OX eta by A gets mapped to A over 1. If that makes sense.
Yeah, that makes sense.
Right, like A is included in K of A.
Yeah.
Um yeah, so that makes a lot of sense. Trick to show that the intersection of two affine open sets may be covered by opens that simultaneously are distinguished in both affine opens. Okay. Thus, irreducible varieties, an important example of integral schemes later, have a convenient property that sections over different open subsets can be considered subsets of the same ring. In particular, restriction maps are always inclusions, and gluing is easy. Functions fi on a covered ui of u glue if and only if they're the same element of the function field. This is one reason why irreducible varieties are usually introduced before schemes. And yeah, that's how Hartshorn does it. But basically, um, like Boolean occurs in K by on U. And in Hartshorn, we saw this as the inclusion map as so. We just didn't really know all of the structure going on underneath it. Okay, so um, I am okay. Let's take a 5 minute break, and then we'll hit the
Okay.
affine communication lemma for the rest of today,
Okay.
or at least set up for it. We'll see. Let's take a 5 minute break. Be back at 11:28.
Okay.
Okay, I'm back.
Uh,
Cool. All right, so what we're gonna do for the next half an hour or so, maybe a little bit more, if I don't know if you can stay,
I got some stuff
is
to take care of. Sorry.
no worries. I never expect you to stay longer. It's just,
Right. And it's just like normally I'd have time, but it's starting to get ready to go back to school.
yeah, I get it. Um, so we'll just do what we can. So, okay, affine communication lemma, properties of schemes that can be checked affine locally. So this section is intended to address something tricky in the definition of schemes. We have defined a scheme as a topological space with a sheaf of rings that can be covered by affine schemes. Hence, we have all of the affine open subsets of the cover, but we don't know how to communicate between any two of them. Somewhat more explicitly, if I have an affine cover and you have an affine cover and we want to compare them and I calculate something on my cover, there should be some way of us getting together and figuring out how to translate my calculation over to your cover. The affine communication lemma will provide a convenient machine for doing this. Thanks to this lemma, we can define a host of important properties of schemes. All of these are affine local in that they can be checked on any affine cover, i.e. a covering by open affine sets. We state this more formally after the statement of the affine communication lemma. We like such properties because we can check them using any affine cover we like. If the scheme in question is quasi-compact, then we need only check a finite number of affine open sets. So proposition, which is not the lemma, but um, let spec A and spec B be affine open subschemes of a scheme X. Then spec A intersect spec B is the union of open sets which are simultaneously distinguished open subschemes of spec A and spec B. And so the proof given by Vakil is given any point P in spec A intersect spec B, there exists an open neighborhood U of P in spec A intersect spec B, which is distinguished in both spec A and spec B. So let spec AF be a distinguished open in spec A wait, in spec A intersect spec B and let spec BG be in spec AF. Both containing P. Then G in the global sections of spec B over the structure sheaf restricts to an element G prime in spec in the global sections of spec AF ox. Um, which is equal to AF. G and G prime vanish on the same points in spec AF. So spec BG is equal to spec AF minus the set of P such that G prime is in P, which is equal to spec AF localized to G prime. If G prime is equal to G double prime mod F to the n, or no, divided by F to the n, where G double prime is in A, then spec AF localized to G prime is equal to spec A F G double prime. And we are done. Yeah. So again, the picture for this is really, if you have spec A, spec B, then, maybe this is spec AF, then this is spec BG, and then here somewhere is P. Yeah. So, does this proof make sense?
Yes, it does.
Dude, what? Can you hear this?
No,
Okay. Well, that's good. They're running and jumping on the floor.
really.
It's
They have a little kid or something?
no, they have teenagers. That's the part. Um, okay. Well, now for the affine communication lemma. Um, let P be some property enjoyed by affine opens of a scheme X, such that for every affine open spec A included to X, if spec A included to X has property P, then for every F in A, spec AF to X has P, and then 2 if F1, this is an ideal, Fn equals A, i.e. spec A Fi cover spec A, and spec A Fi injects to X, has P for all I, then so does spec A to X. And then suppose X is covered by spec AI, where spec AI has property P. Then every affine open of X has P2. So this is just a very nice, very, very, very nice lemma. So as a definition, a property P satisfying 1 and 2 is called affine local. One motivation for this name is that by this lemma we can determine if every affine open subscheme has the property by checking on any affine cover. As an example, reducedness is an affine local property. More generally, any property that is stalk local is necessarily affine local. So let me go ahead and write that down. Prop stalk local implies affine local. Where an affine scheme has the property. Okay. It is sometimes not so obvious what the right definition. Yeah. Yeah. Okay, and the proof of this is okay. Hold on. The proof is so easy. Um, let spec A be an affine subscheme of X. Cover spec A with a finite number of distinguished opens spec AG, each of which distinguished in some spec AI. By one each spec AGJ has P. By two spec A has P. And that's the whole thing. Which that is like the easiest, nicest proof ever.
Yeah.
So by choosing the property P appropriately, we define some important properties of schemes. So proposition A be a ring, and the ideal F1 covers A. One, if A is Noetherian so is AF. If each AF is Noetherian, so is A. If B is a ring and A is a B algebra, if A is finitely generated, then so is AFI. If each AFI is finitely generated via algebra, so is A. And when we say B algebra, we mean like polynomial ring over B for the most part. So if A is like if your polynomial ring is finitely generated, then each like index of it is and localization is finitely generated, and back and forth. Results assuming that this is true. So it says that we will prove this later. Um, so as an important definition, um, if A is a ring, no. If X is a scheme covered by affine opens spec A, where A is Noetherian, we call X a locally Noetherian scheme. And then if X is quasi-compact, um, X is a Noetherian scheme. Quasi-compact, again, just meaning that we can cover it with finitely many affine opens.
Yeah.
So Noetherian equals quasi-compact and locally Noetherian. Um, yeah. Important. What the heck? Important theorem. So locally Noetherian schemes are quasi-separated. Um, so the intersection of any two quasi-compact open subsets is quasi-compact. So intersection of any two quasi-compact sets is quasi-compact. And so then the intersection of locally Noetherian schemes is a Noetherian scheme. Um, and then a related theorem is that A Noetherian scheme has a finite number of irreducible components. Um, as well as connected components. Okay. I think this is where I want to stop for today.
Okay.
And where we'll pick up tomorrow is with varieties, normality, and factoriality. Fact, factoriality. Factoriality. There we go. Um, yeah. And then that'll take us into some arithmetic results, which are kind of nice. And
Hmm.
then we will pick up on Saturday with quasi-coherent sheaves.
Okay.
And then we will be back at school.
Yep.
Cool. I'm going to go ahead and stop the recording.
All right.